Now we can take a look at these hardware performance counters that are already teased, where we can look at a lot of these metrics that are measured by the CPU architecture itself, by the CPU, and then we can use these metrics to figure out our what bottleneck. As explained, there could be multiple bottlenecks in at the same time in your program, and they limit your performance. So there could be a problem with the interconnect if you have many requests between the CPU sockets, or it could be limited by the memory bandwidth. Therefore, you have unfortunate or memory request patterns. Um, Maybe a misuse of the cache. Maybe there could be something improved there, or the thread parallelism, and so on. And we can use this liquid tool to, so this is a command line application that helps you to access these metrics, then to figure out where the bottleneck is in your application. So the command is, if you load the module liquid minus performance counters perf ctr, and here you basically specify which metrics you're interested in, run the program, and it will at the same time then read out these values from the CPU, and then you can take a look what happened during the execution. There are multiple operation modes to get a closer look at what happens. So there you can see these groups. These are groups of metrics, and you can list this the list of the metrics that are available for your CPU architecture. So the tool knows multiple CPU architectures. And here you see, for example, you can look at the number of floating point operations. You can look at the bandwidth that was used by the caches during your the execution of your program, and so on. And then you basically say liquid perf counter minus G and the group, in this case CPI, and then if we look at the specification, then we see there are some of these event counters used. Therefore, the CPU offers multiple metrics, but you can't measure all of them at once. You only have a limited number of metrics that you can measure at the same time, because they have to be stored in some physical counters in the CPU, and they have just more possible event sources, for example, the number of instructions or from the cache and so on, that can be counted, but only in a limited number of places where they are stored. Therefore, you can specify some of these event counters, and then there are also some derived metrics specified here in the group specification of Liquid. Therefore, Liquid accesses or reads out these values and then derives some further values here. And we can run Liquid perf counter with the CPI group. Therefore, cycles per instruction. Minus C7 means it should be pinned to this core. It will only be executed on this core, and the values come from this core, the performance counter values. And we are doing a sleep, and then we see how many clock cycles were executed, and the retired instructions, and it also always measures the time. Therefore, here in the end, we see our program took a little bit more than 10 seconds. We had a certain frequency, certain number of instructions, and from this, we see that we then have an CPI, or the reverse, an IPC value here of how many cycles per instructions were used, or how many instructions per cycle could be executed. And if we run this for CPU stress test program, then we see that we actually have more instructions per cycle than it was actually executing some instructions and um, doing something, and then we have a different value here. There's also, so Liquid has a lot more features. We have this benchmark feature where there are specified some assembly instructions that are executed to assess some certain things. For example, some floating point operations or some memory requests here that can be used as a benchmark of the system. And so here we basically can combine the performance counters accessing the measurement and the benchmark execution, and then yeah, look at the metrics when the benchmark is executed. And we have this marker API, which allows to, so Liquid works with any program. So you can give it just a binary executed, and Liquid then reads out the CPU counters, but you can have a more in-depth look inside of your code. If you can recompile your code, you can add some certain markers, then the Liquid library is included to your program, and it will talk to Liquid. And this way you can more precisely look at the behavior of a certain part of your code. For example, you have some initialization phase, and then you have your interesting part of the code, and then you have some finalization phase. You can, using this marker API, only look at the performance metrics for this important part of your code. But for this, you have to recompile your program. Yes, exactly. You have to add the Liquid library, link it to your program, and then add these instructions. Then you could have multiple regions, and Liquid then will put out the performance metrics for all of these regions in your code. So this allows for a more in-depth analysis of your program performance. Now we've seen it's important when you want to optimize and get the very best performance on the system, you have to understand the how the system is actually working. Because if you have a bottleneck in your application, you want to figure out what is happening in during the execution of your program in the CPU. Where is the performance not as good? For example, the cache wasn't used as well, or I did not create or executed as many floating point instructions as would be possible. Why is that? Where is the bottleneck during the execution of the program in the CPU pipeline? And using this analysis techniques, you can then look at the performance metrics and figure out where the performance problem could be, and then concentrate your optimization of the program to get rid of this bottleneck. At this point, do you have maybe some questions? Yes.
Just out of curiosity, maybe you're gonna go into it during the hands-on, but you were talking about branch prediction and how a wrong prediction can um, lead to performance um, um, to worse performances. Do you have an example on how someone can optimize towards that, or make the mistake of running into that problem often, regularly?
So the question was if, for example, we have a branch prediction and there's a problem with this, how what would be an optimization technique, and so the metrics that you can measure depend on the CPU, and for I'm not completely sure. You have to look it up in the actual available groups and metrics for the architecture, but there are some detailed counters depending on architecture. So the Noctua 1 had it. I'm not sure about Zen 3, but Zen 5 and the Otus will also have it, where you can also have a counter of the um, false branch prediction, and then you can figure out, okay, if I'm looking at this code or looking at this code, looking at this code, where did these wrong branch predictions take happen? And a wrong branch prediction always can only happen if you have a conditional jump. Therefore, one technique would be to get rid of the conditional jump. Therefore, sometimes you can think about how can I make the code paths independent of the condition. So this, if you, for example, if you're working with integers, then the instructions are rather cheap. And if you have now a condition that says where you check a flag, if it's 1 or 0, and depending on this, you will do something with some values. What you can do is, instead of checking the flag and then have a condition where you have to jump to some code, you can multiply with the flag. Because if you, for example, have some value and then multiply with a 0, it will become 0. And if it's 1, then it stays 1. And then you can use this value further if it fits with your code logic. And this way, you don't have to have a comparison if this is a flag 1 or not. You just do the multiplication. You always do the multiplication. And depending on the flag, the value changes. And this way, you can get rid of this condition, this check, and then you don't have a jump anymore. So this is one example.
Thanks.
Mm, Also, sometimes it depends on the structure of your loops and the checks. Sometimes you can change a little bit the structure, and then it doesn't really change the logic, but to change how well the CPU can predict the condition. So that there's some ways uh, to optimize this. Yeah. In the exercise, we prepared some programs that are doing matrix multiplication. There are multiple variants of the program, and the idea would be to measure it. So you can run it with multiple sizes and of the matrix, and they behave differently, they're programmed differently, and you could then use Liquid inside of your job to measure some performance metrics to compare these variants. And if you have any other questions, we are here during the hands-on, and we are happy to answer your questions. All right. So as you have maybe um, experienced, so this time wasn't that enough to do a very thorough analysis. It's just more to get familiar with the tool, to run it, and so you can run the mm, example script and then see that we load our liquid module because we needed to get this command, and then I can specify the group and pin it to one core, so we have only the values from one core, and then run the here's the command that we actually want to execute our program, and then we have our parameters for our job, and here I'm using minus minus exclusive, so there's nothing else or no other user's code is running on the compute node. So we have the complete node for ourselves because this is basically a benchmark. We want to measure the behavior of the program, and so we don't have as little interference as possible. And also the collectors are off, so this is for a job monitoring system because there could also be a conflict because it also uses these counter counters. Therefore, we want to turn them off. And let's see. And then we get the similar output as in the slides. For the CPI group, we have our raw values, and then we have our derived metrics here, the runtime, clock, CPI, IPC. And now I copied the prepared binaries. And what they're doing is a matrix multiplication, and they basically take the size of the matrix that is used. So we want special sizes. This is more of a test code here, and then we can it will create some matrices, do the multiplication, and then print the time. It was 6.6 seconds, and depending on which variant you're running, it has different times here. So this is exemplary. If you would do a real analysis, you would do multiple runs to see like the variance of the metric and so on. But in this case, we already see the first one is quite slow. It takes 6 seconds, and the last one is apparently the fastest. It only takes 20 milliseconds to run basically the same calculation. And then we can do another job script where we, for example, have the flops metric measured, and here in the bash script we have a loop that simply loops over all of the variants and measures the flops metric, and then writes the output of the measurement into this file, variant number underscore flops dp, and this is what we have here. And if we take a look at one of these files, we see it's now in a CSV file, and we see here the derived metrics here at the bottom. And I can print these example results here for all of the variants. So the metrics CPI and double precision, floating point operations, and we see if it's the same number of operations and the first program takes 6 seconds and the last program takes 20 milliseconds, then it has a multiple of the floating point operation number per seconds, because it's basically the same. For the matrix multiplication, you have to do a certain number of operations, and if you take a way longer time, then the same number of operations will then result in a way lower rate of operations per second. And here we see that we only achieve 302 megaflops per second on the first variant, and 66 gigaflops in the last variant. And we also see this also has an effect on the CPI value, and then there's some variance in between here. And if you then do some other measurements, I did them beforehand, and here we see different sizes of the matrices, and then we have different flop rates. So here we see the variant, then the size, and the flops. And okay, here this was basically there was a problem with the measurement. So this is invalid, but for the other ones, we see that we reach here 106 gigaflops and very bad performance in the first variant. And we also see here for the different cache levels, the cache miss ratio. Therefore, here in the level 1 cache in the first variant, we see a 30% ratio of misses in the cache, level 1 cache. And in this case, it has to go to the level 2 cache, and then it also has a certain rate ratio of how many misses and non misses there were in the cache. And if we compare it with the last variant, then we see the ratio of successful requests to the level 1 cache here is far better in the last variant. So apparently the last variant is way better in utilizing the cache in, so the memory access patterns are more beneficial for how the cache works. Okay, and we see it also depends on the size, because depending on the size, it the complete matrix fits in the cache or not, and then it will basically um, has to store also some values in the and go to the other cache to read the values there.